So I'm going to talk about a fixed block memory manager. This is particularly in an embedded systems context. I designed this fixed block memory manager when I was working on an embedded Linux project. Uh, and I'm just going to give a brief overview. At some point, I'll make the source code available for it. Um, and so I'm just go ahead and get started. So, first off, the design. This was supposed to be a three-level memory manager. We have the master that just held the number of partitions. It also held the array of memory partitions. In each memory partition, there was buffer size, number of buffers. We had the actual buffer space, which I've got referenced here as array of buffers. We to speed it up a bit, it ended up being a void pointer for this next available buffer. So it was easy to check the memory pool, grab the next buffer if there was one. Otherwise, it would go up to the next available size, so we wouldn't eventually run out of memory. The memory space start pointer and end pointer, that is for checking to make sure that whenever we're freeing a buffer, and it goes back into the correct memory pool, or if we happen to allocate memory outside of these before this memory manager is initialized, then we know that it's not within any of these pools and we can release it normally. So, as an example, say that we wanted to set up just one of these memory partitions, buffer size 8 bytes with 8 buffers. You can see in the array of buffers that we have a starting address of 600,000 hex, and the start pointer of the last buffer is 600,038 hex. Um, how that affects the rest of this, you can see the position in the array is 0. So we're looking at the first position in the array. That is going to be our next available buffer. And also, it's going to be our start pointer. You can see also that the end pointer is 600,040 hex. That is different than the start address of the last pointer. That is the end position of the last buffer. So we know that any address between that 600,000 hex and 600,040 hex is within this memory pool. So whenever we're looking at any of them, we know immediately that, hey, this is inside this pool and we're good to go, whether it's allocating it, freeing it, whatever. And we move on. So after we've allocated a few, we can see the position in the array is 3. We update the next available pointer. The start and end pointer do not update. Those are should be static values that we should not change within this memory manager. Um, each memory partition is going to have different values there, but those don't update. The next available buffer, the position in the array, and the array of buffers will update as we move along, are allocating buffers, freeing buffers, whatever. Um, so now I can get onto the implementation. In the master, ended up needing, and this is all stuff that was going to be used in a production device. So there are a lot of metrics and other variables that we used for fine tuning it. They may not be necessary in your system. It's entirely up to you. A lot of them are going to be in here in this example, and I can talk about them briefly, but the main idea is to get the understanding of the fixed block memory manager. Um, so the top level of this memory manager is the mem master. Got it here. We have the number of partitions, logging level. If, if you want to set logging to debug, verbose, error, whatever. If you need more explanation about that, then I can talk about that separately. Um, the options struct is going to contain a bunch of options about the memory manager. I'll get into that in a different slide. And then the actual memory pools are going to be in this struct partitions. You can see it's an array of pointers, and I'll explain further as I get along into this. All right, so here are the options: check alignment, check stack, enable asserts, audit to the console, audit to the syslog. I've got another slide, I'll talk about them, but this is just an overview of the actual implementation that I did while I was working on this. Each partition has it's a variable length. There's up to max parts partitions, but this could also be made into a double pointer. So we allocate all of the space, and this could be however many partitions you need for your system. Um, so each partition has a config struct, which contains information about each partition, things like the number of buffers, the size of all of the buffers. I'll get into that. I implemented this as a stack instead of just an array, and then I've got some visuals and code later on that can kind of show that. Uh, like I talked about previously, the buffer space start and end, and the position within it. And it's going to be the same for every partition. The config struct will change. The stack pointer in this is the next available pointer. So talking about the options for the memory pools. Check alignment. We wanted to make this extremely robust. This was for an embedded device that was time sensitive and critical. So we wanted to ensure that while we were testing, that we had that all of the buffers were aligned with the memory partition that it was pulling from. Um, so we had it while we were debugging. We had this check alignment set to enabled check stack. We wanted to make sure that we didn't have any kind of synchronization issues of allocating or freeing uh, the same pointer, or that same pointer wasn't being given to multiple threads that were trying to use it. All of these Alex and freeze were wrapped in mutexes, so it was very unlikely, but we had this enabled just as we were debugging so we could check it all. The next variable is an assert. For enabling the assert, we wanted to be able to break whenever we ran into an issue if we did. So if we ran out of buffers in this pool and we knew we needed to increase the number of buffers, then we could set this assert and say, all right, cool, we ran out of buffers. This pool is empty. We actually need to increase it instead of just going up to the next size. Um, it also would assert if there was any alignment issues or stack check issues. And then part of that checking was, are we going to audit all of these Alex freeze initialization, whatever, to the console port, and then also audit to the syslog or log file, whichever one. It's all just things that we use for debugging. Okay. And now actually getting into each of the memory partitions, you can see in a partition that config struct just held. This was done for uh, configuration's sake and making it a little bit easier to read. Had its own struct. Doesn't necessarily need to be in its own struct, but this is the way we did it. Uh, Buffer size, the number of buffers, and then audit. So we could, at each pool level or each fixed block pool, we could audit whenever we were allocating, whenever we were freeing, whenever we were initializing. There's some other stuff that I didn't put in here about metrics, but it'll be in the main source code that I make available at some point in the future. Um, so yeah, it just held the information about the partition. It was easy to check. Say, okay, we need just say an 8 byte buffer. We'll go in, check. All right, are we in the correct partition? It's easy enough to check against that buffer size variable. Um, like I talked about previously, the stack pointer, buffer space start and end, and the position. I think I've explained those enough. If I haven't, let me know. I can go further into it later. And I'll do a separate video about what a fixed block memory manager is if it's unclear to anybody. As we would allocate, we'd pull a buffer off the stack, increment the position, and then update the stack pointer. If there were no buffers left, then that stack pointer would end up being null, and that would be a very quick way for us to look at the buffer pool, say, all right, we're out, move to the next size, and we can continue. Here's some of the code. This is just for the initialization. Each of the memory config structs, we this is just a small snippet of it. We wanted to create an individual struct for each memory pool size. So here we've got an 8, 16, 32 byte pools that we were going to end up making. There's several others, and you can see the number of buffers in each one of them, 128 or 256. This was quite complex system, so we needed a lot of buffers in these smaller pools to handle a lot of configuration values and things. Not important right now. Um, so each of these memory config structs were put into this struct here, this memconfig mempool struct array of pointers, and starting from the smallest going to the largest, and the last one was always null in here, so we knew that we were done. This was the way that the initialization code would go through and take all of the information about that pool and go back through, allocate the correct amount of space, set up all the correct structs, and then place it into the pool. There's a separate struct here for the memory options. That was all the ones I talked about of checking the alignment, stack, asserting, and then the logging. How this would be used, at least for initialization, we would create a variable here that you can see num pools, and we'd take size of mempool divided by the size of a pointer of mempool, and that, I mean, that's referencing the first element in the mempool. So we would get the number of pools that we were setting up, call the memory initialization, pass it this plus the number of pools. I forget what that log none was for. I don't know if that was just for logging the initialization or if that was an error message, but I'll review the code and make it clear whenever I make the source code available. That's basically it. This is just a quick overview and of the design of the memory pools of the fixed block memory manager. And you can see here, this was this is just one way to do it. There are many other ways to do it. It's software. There's a million different solutions. It just depends on the ease of writing it, the ease of maintaining it, and then also that it's correct. But like I said, there's a million ways that it's can be correct, and really just depends on efficiency. So if you like this, want me to do some more of them, let me know. But I will, like I said, I will make the source code available at some point and update the description here with that. It should be a drop-in ready library for the memory that anybody can use for theirs. They just have to work on the initialization. So let me know. Thanks for watching.